So now let's look at some nice properties that radon measures enjoy. Nice properties of radon measures. So first is that, so let me write this as a theorem. If X is a locally compact Hausdorff space and mu is a radon measure on X, then the space of continuous compactly supported functions is dense in L1 X mu, meaning that given any epsilon greater than 0 and f in L1 X mu, there exists G epsilon. So this G depends on epsilon, which is a continuous function with compact support, such that the norm of f minus G epsilon of L1 norm, this is less than or equal to epsilon. So we have already seen that in RD with the Lebesgue measure, this kind of result holds, that CCRD is dense in L1 of RD with the Lebesgue measure. But now if you have a radon measure mu, then also this kind of result holds. So let's see a proof. The first thing to note is that since simple functions are dense in L1 just by the definition of the Lebesgue integrals, it suffices to prove the result, for f equals the indicator function of E, where E is a Borel set with finite measure. So mu E is finite. So if we can prove this for indicator functions of Borel sets with finite measure, then we can easily do it for any general L1 measure by first taking finite linear combinations of simple functions and then approximating in L1 norm by simple functions. So now we need another result. So I claim that if E is a Borel set such that mu E is finite, then mu is inner regular for E. So note that the radon measure assumption is only that mu is inner regular for open sets, but now I claim that for any Borel set with finite measure, mu is inner regular. So let's see why this is true. So we have to show that mu of E is equal to the supremum of mu K such that K is compact in E. So to do this, first we use that E is a Borel set, so mu is outer regular, for E, which means that given epsilon greater than 0, there exists an open set U containing E such that we have mu U is less than mu E plus epsilon by 2. So this is just by outer regularity, of mu for Borel sets. So this means that mu of u minus e is less than epsilon by 2, and in particular this is a Borel set. So this implies that there exists an open set V containing u minus e such that mu v is less than epsilon by 2, again by outer regularity. So we have first chosen an open set containing E such that mu u is less than mu e plus epsilon by 2, and then we chose an open set V containing u minus e such that mu v is less than epsilon by 2. Now by inner regularity, for open sets we have that mu is inner regular for u, which means that there exists a compact set K compact such that mu of u is less than mu k plus epsilon by 2. Now take F to be the set K minus V. So remember that V was an open set. So this is equal to K intersection V complement, and since K is compact and V complement is closed, so this is compact. So this set is compact, and F is a subset of E. This is because V covers u minus, V is u minus e is contained in V. So F is in fact contained inside E. And finally we have that the measure of F, mu of F, is equal to mu k minus mu v, but mu k we can use this inequality. So from 1, this is 1, which says that mu k is greater than mu u minus epsilon by 2 minus mu v, but mu u is greater than mu e by monotonicity, because E is a subset of u. And then we have, because mu v is less than epsilon by 2, this is greater than mu e minus epsilon by 2, which is mu e minus epsilon. So this means that we have found a compact set which is greater than mu e minus epsilon, which means that mu e is the supremum of mu f, such that f in E is compact. So once we have shown this, it's easy to show that we can find a continuous function with compact support, which is which approximates the indicator function of a Borel set in the L1 norm. So now we have to show that there exists, given epsilon, there exists G in CCX such that the L1 norm of chi e minus G is less than or equal to epsilon. So now we can use the fact that mu e is finite implies that mu is inner regular for E, and this means that there exists a compact set K in E and an open set U. So this is compact and this is open, such that mu u minus k is less than or equal to epsilon, because by inner and outer regularity. So this is by inner and outer regularity. And then we can find by Eurizone's lemma there exists a continuous function with compact support such that we have k less than g less than u, which means, so in our last lecture we used this notation to mean that g takes values between 0 and 1. Support of G is compact. G is identically equal to 1 on K, and support of G equals is a subset of U. So G is 0 outside U. So by Eurizone's lemma we have this, and we have seen that this is equivalent to saying that the indicator function of k is less than or equal to g, and this is less than or equal to indicator function of u pointwise, meaning that g can be sandwiched between the indicator function of k and the indicator function of u. So now we can estimate chi e minus g, the L1 norm, and this is nothing but the integral of chi e minus g mod d mu, and this is less than or equal to integral of x over x chi u minus g d mu, since chi e is less than or equal to chi u, and this is nothing but, now chi u is always greater than or equal to g, so we can lose the modulus sign. So this is equal to chi u minus g d mu, and now this is again less than or equal to chi u minus chi k d mu, and then this is nothing but the mu of u minus the mu of k, and this is less than or equal to epsilon. So we see that continuous functions of compact support are dense in the L1 norm, are dense in the L1 functions, the space of L1 functions on X with the Radon measure. And so once we have this, as a corollary, we have Lusin's theorem, which says that if X is a locally compact Hausdorff space and mu is a Radon measure, on X, and if f is a measurable function, is a Borel measurable function on X, so f is a complex valued Borel measurable function, then I need another assumption that such that f is 0 outside a set E, a Borel set E of finite measure. So again we would need inner regularity. So outside a set E of finite measure, f is 0, so support of f is contained inside a set of finite measure. Given any epsilon greater than 0, there exists a Borel set A such that the measure of A is less than or equal to epsilon, and f is continuous on E minus A. So this is a generalization of the Lusin's theorem that we have seen for Rd, two locally compact Hausdorff spaces but with a Radon measure, and the proof is essentially just a repetition of the proof for Rd, but taking into account that we have a Radon measure and we have chosen f to be to have support inside a set of finite measure, and then we can basically repeat the proof, but this is left as an exercise to check the details of this proof, check the details. So then we get Lusin's theorem for locally compact Hausdorff spaces with Radon measures.